I'll demonstrate that finite fields have prime characteristic. So let's call our finite field f, and let's define the characteristic to be the smallest number such that the following equation holds: n times 1 inside f is equal to 0 in f. So in other words, we sum 1 n times, and we have to find 0. So the smallest number f for which this is true, so the smallest number n for which this is true, is called the characteristic. So to demonstrate that a finite field has prime characteristic, we'll look at the ring homomorphism from the integers into the field f. And we map, as before, n into n times the unity in f. So then this is a ring homomorphism. And therefore its kernel is an ideal. And we can divide the ring by the ideal and find a ring which is isomorphic to the image. So image of f is certainly a subring of the field. And as a subring of a field, it is automatically an integral domain. Because we cannot find two elements in f even whose product is 0 and which are not, where one of them is not individually 0. In other words, this is a, b is 0, then a is 0, b is 0. And since this is true in f, it's automatically true in a subring, and therefore the subring is an integral domain. But if imf is an integral domain, then automatically in such a construction, the kernel of f will be a prime ideal. To understand a bit more in detail that the kernel of f is a prime ideal, let's suppose that the kernel of f contains the element n times m. Then nm times the identity in f would be 0. We can clearly see that this implies that n times the identity in f times m times the identity in f is 0. And therefore, because we have an integral domain, it has to be the case that either n1 nf is 0 or m times 1f is 0. And therefore, really also n would be an element of the kernel of f, or m, and so on. Such that we can always further divide. And in the end, we wind up with the fact that the kernel of f has to be a prime ideal. But prime ideals in the integers are just pz, where p is prime. So Pz is the kernel of F, and therefore the image of F has order P and is in fact a subfield of our finite field F. But that means that F is actually a vector space of MF of order P, where P is a prime. But this means that if I draw F as a vector space, for instance like this, finite dimensional vector space of dimension 2 in this case, where one side has length P, and I could do this in n dimensions. So if the finite field F is a vector space over MF of order P, this then means that the dimension of the finite field F equals a power of P, where P is prime. So this is a direct consequence of the fact we proved earlier, which is that the characteristic of the finite field F is P, where P is prime.